everyone and welcome to No Waffle A-Level. In this video we are going to be going over the fifth video of the electricity series, drift velocity. Here are the three key things set in timestamps but also use it as prompts for active recall. So let's look firstly at what is drift velocity. Drift velocity, in terms of the exam definition, is the average velocity of charged particles in a material due to an electric field. So it's looking at the displacement of the electrons from its starting position over time, how they're moving because of the electric field, because of the EMF. So how fast the electrons are moving towards the positive terminal. So no voltage or electrical field applied, the electrons are moving like that, which is called random thermal motion. But when there is an electric field applied, it looks like this. All the electrons are moving battling through the metal ionic lattice, trying to get towards the positive terminal, because suddenly, as soon as the electric field is applied, it gets magnetized and it wants to go towards the oppositely charged, therefore positive, terminal. Since the electrons are always colliding, they do not travel in a straight line, so the average speed at which they're moving is referred to as the drift velocity. Because, as we said, it's really hard to find how fast this one's going if that one's going and colliding into something. So the drift velocity is the average velocity of the charged particles. Let's look at how we can derive the drift velocity as an equation. So this is a cross-section of a wire, okay? You've got the shaded section, which is the area, and you've got a point. You can see that there's an electron trying to move from this point to that point. So let's say that V is equal to velocity, T is equal to time, D is equal to the distance required to travel, and the volume, as we know, volume is always going to be equal to the cross-sectional area, this area here, multiplied by the distance to find the volume between these two bits. Now, we know that velocity is equal to the distance divided by the time, so therefore it can be rearranged that distance is equal to velocity multiplied by time, and therefore we can rewrite the volume equation over here, because we know that distance is equal to velocity times time, so we know that the volume is equal to the area multiplied by the velocity multiplied by the time. Now let n equal the number of electrons per unit volume. For example, n here is the number of electrons per meters cubed, for example. Now the total number of electrons, if we wanted to write an equation to get the total number of electrons, it would be the volume multiplied by the number of electrons per unit volume to get the number of electrons within that volume. The total charge would therefore be the number of electrons multiplied by the charge on a single electron, which is denoted by this letter E. And the charge on a single electron, you should know this from a previous video I did, is minus 1.6 times 10 to the power of minus 19 coulombs. Therefore, current is equivalent to charge divided by time, as you can see there. And therefore, if we were to write it as that, we know that current is equal to the total charge, which is this equation, divided by time. And you can cancel out the time, so you know, therefore, that current is equal to the area times by the velocity times by the number of electrons per unit volume times by the electronic charge. And the V could also be drift velocity as well. So that's how we derive the drift velocity equation. It's really nice. This is a really nice derivation, so I'd recommend you look into it, and we'll look into a lot more in the course of physics as well. Now we'll look at how fast is drift velocity. Drift velocity is really slow. And the reason why is because the current in a circuit is actually equal to the charge times the velocity. So the charge of the electrons in a few centimeters is very large. So what it's basically effectively saying is when we're talking about current, we're less caring about how fast the electrons are going, but more caring about how much overall charge there is that's collectively moving. Even if it's moving a thousandth of a millimeter, if a lot of charge is moving, then that counts as a large current. But naturally, you need to know that electrons move really, really slowly. Like it could take up to a year for electrons to move from the negative terminal to the positive terminal. That's how slow it is. But what current is talking about is the overall charge that's moving. So, if drift velocity is so slow, then how do things like flashlights and light switches turn on so instantly? Well, it's similar to what we just said. The changes in the electric field transfer the speed of light, so that electric field is very rapid, and because that then causes everything in the wire to suddenly become electrified, and it all of the electrons then start moving at the same time. And because there's an enormous amount of electrons all moving simultaneously, there's a very large current causing a large charge, causing a very significant current. So you need to remember that current is talking about the amount of charge, not the number of electrons moving. So thank you so much for watching this video. If you found it helpful and fun learning about drift velocity, then why not check out some of my other YouTube videos in which I use similar animation. I put a lot of effort into these videos, so it would mean the world if you could share this with your friends. Have the best day and do the best in your exams that I know you can, and see you soon.